Have you ever stared at a really complex chemistry problem and just thought, where do I even start? Well, today we're going to crack the code on a few of them, step by step, and you'll see how just a couple of key principles can unlock even the toughest questions. Okay, let's dive right in. So, you ready to feel a little more like a chemistry pro? We're going to break these problems down into simple, easy-to-handle steps. Seriously, you'll be amazed at how much you can figure out with a bit of logic and the right approach. All right, so here's our game plan. First, we'll tackle some reaction kinetics. Then, we're going to play detective and identify a few mystery organic compounds. And we'll wrap things up by using titration to check a chemical's purity. Let's get started. Okay, our first challenge is all about kinetics, the speed of reactions. We've got this unknown alcohol, and our mission, first and foremost, is to figure out exactly what it is. After that, we'll track how fast it reacts. This is where we really get to see chemistry in motion. Now, the problem gives us this massive clue right at the beginning. We're working with a secondary alcohol. So what does that mean? It just means the OH group, the alcohol part, is stuck onto a carbon that's connected to two other carbons. You're going to want to file that detail away. It's going to be absolutely crucial a little later on. So, where in the world do we start? We start with this one number, 26.67%. That's how much of this alcohol, by mass, is just oxygen. It might not look like much, but believe me, this is the thread we're going to pull to unravel this entire molecule. The process here is just pure chemical logic. We know the general formula for a saturated alcohol, right? It's CnH2n plus 2O. All we have to do is set up a simple equation using that formula and our 26.67% oxygen clue. From there, we can solve for N, which is the number of carbon atoms. And when we run the numbers, boom, we get our answer. N equals 3. Just like that. This tells us our mystery alcohol has a 3-carbon chain. That's a huge piece of the puzzle right there. So, if N equals 3, the formula must be C3H8O. But wait, remember that first clue? That it's a secondary alcohol? That means the OH group has to be on the middle carbon. And that tells us its exact identity, propan-2-ol. See how that one little detail made everything click into place? Okay, now that we know what we're dealing with, let's watch it react. When propan-2-ol is oxidized, it creates a product called propanone. This table here shows us exactly how much propanone is being made over time. We're literally watching the product concentration grow, minute by minute. And if you're a visual person like me, check this out. When we plot that data, concentration versus time, we get this beautiful classic reaction curve. You can see how the reaction is super fast at the start and then starts to slow down and level off. This graph is basically the story of our reaction's speed. So this brings us to a really important idea in kinetics, half-life. The simplest way to think about it is this. It's the time it takes for something to get halfway to its final state. In our case, since we're watching a product form, the half-life is the time it takes to create half of the total propanone we're going to end up with. It's a super important measurement for everything from medicine to nuclear physics. And finding it on our graph is actually pretty easy. You just find the final concentration, cut that value in half on the vertical axis, and trace a line over to the curve. Then you drop straight down to the time axis. And for our reaction, we find that the half-life is 2.8 minutes. We just put a hard number on the speed of this chemical change. How cool is that? All right, let's switch gears for our second challenge. We're moving from kinetics to identification. I want you to imagine you're in a lab with 4 unlabeled bottles. Your job? Figure out what's in each one using just a few simple chemical tests. It's a real chemical whodunit. And here is our evidence board. This table lays out all our clues. It shows the results from 3 different tests on our 4 mystery compounds, A, B, C, and D. Every single result here, every color change, every solid that forms, is a vital piece of the puzzle. So let's focus on A and B for a second. Look, they both react with NaHSO3 to make a white solid. That's a classic test that tells us they both have a carbonyl group. But here's the kicker. Compound A turns that bright purple permanganate solution colorless, while compound B doesn't. That second test is our tiebreaker. It's what lets us tell an aldehyde apart from a ketone. And just like that, the case is cracked. Since A reacts with permanganate, it has to be the aldehyde, butanol. And since B doesn't, it must be the ketone, butanone. See?
2 simple tests, and we've solved half the mystery. That's the power of qualitative analysis right there.
Okay, on to our final challenge. And this time, we're not just identifying a chemical, we are measuring it with some serious precision. The goal is to figure out the purity of a commercial sample of sodium hydroxide using a technique called titration. This is a huge deal for quality control in pretty much every industry you can think of.
So the problem gives us these 3 possible graphs. Each one shows a different way the pH might change as we add hydrobromic acid to our sodium hydroxide. The thing is, only one of these curves can possibly be correct for this specific reaction. So take a quick look. Which one do you think it is? Just think about it for a second. What are we starting with? A strong base. And what are we adding? A strong acid. What should that pH journey look like on a graph? Okay, let's trace the story of this reaction. We're starting with sodium hydroxide, a strong base, so our initial pH has to be really high, right? Way above 7. Then, as we add the strong acid, the pH starts to drop. The biggest, most dramatic plunge happens right at the equivalence point. That's the moment when the acid has perfectly neutralized the base. And for a strong acid, strong base reaction, that happens at a perfectly neutral pH of 7. After that, we keep adding acid, so the solution gets acidic and the pH bottoms out. Only curve B tells that exact story. Now, by taking the amount of acid we use to get to that equivalence point on our correct curve, we can do a calculation to find the purity of our original sample. And the answer comes out to 39.6%. This is a perfect example of how chemists use titration every single day to verify the quality of a product. All right, let's just zoom out for a second and look at what we've accomplished today. We've really worked through 3 totally different but super important kinds of chemistry problems. We started off with kinetics, using it to not only identify a molecule, but also to measure exactly how fast it reacts. Then we put on our detective hats and used some basic chemical tests to solve a 4-part mystery. And finally, we used the precision of titration to check the purity of a real-world sample. You know, these aren't just exam questions. These are the fundamental skills that working chemists use all the time. And that's a wrap. But I want to leave you with this one thought. These exact methods we use today are how scientists make sure our medicines work, our food is safe, and our environment is clean. So the real question is, now that you've seen how it's done, what real-world problems could you go out and solve? Thanks so much for joining me.